started. So today we're going to continue in the lecture sequence on linear regression. And we're going to be talking about residuals, which is basically a way of talking about the errors in linear regression. So to situate you where we're at, we've been talking about how to find the best fit line, the linear regression line. In the past, we talked about errors and how to measure how much error there is, how much error you will have in the predictions that you make if you use linear regression to predict values. And today, we're going to be looking more at those errors and looking at the size of them and how they relate to the correlation coefficient. Okay. And then on Monday, we'll be looking at some more at making predictions. When you make a prediction, understanding how much uncertainty there is in your prediction. Okay, so announcements. Don't forget homework due today. Also project due today. So hopefully you got a real good start and you're almost done, but don't forget to finish off. All right, so a refresher from last time, we talked about errors. We use a linear regression to make a prediction. And the error is the difference between the actual true value minus the estimate, the prediction we made. Okay, errors can be either positive or negative. And a way to measure the rough size of the errors that we've been using is this RMSE. And so to compute the RMSE, you compute the error for every point. You square all of those errors. You take the mean of the squared error, and then you take the square root of that. So root mean squared error. You take the errors, the square of the errors, the mean of those squared errors, and then the root of that. And that gives you a measure of how large the errors typically are, and therefore a measure of how good your regression line is as a way of making a prediction or an estimate what the true value will be. Okay, so in linear regression, the standard name for this word error is residual. It's the same thing. It's a synonym. If you see the word residual, you'll know that's referring to the error. The residual is the error when you're doing a linear regression estimate. Okay, so for each point, each data point, we have a residual. And the residual is the difference between the actual observed value of y, the thing we're trying to predict. Y is the thing we're trying to predict. So it's the difference between the actual value of that minus our estimate of that. Remember, the estimate we're using or the prediction we're coming up with is based on the linear regression line, on the best fit line. So this is the difference between the actual value of y and the prediction you would get from the line. Okay, so the prediction you get from the line is the height of that line at the x value. So this is the difference between the actual point and the height of the line. It's the distance between this point and the line, the vertical distance between the point and the line. That's the residual. Okay, residual, again, like an error, it's the same thing, can be positive or negative. If it's positive, that means that the actual value was larger than our prediction, so our prediction was too low. And if it's negative, that means the actual value was smaller than our prediction, so the prediction was too high. So let's look at an example. Let's do demo. Okay. So we're going to work with this data set that has information about congressional districts in the 2016 election, showing in each district the median income in that district and the percent of people who voted for Clinton. I wasn't able to get an updated version of this for this 2020 election, so we're working with this older data set. Okay, so the residuals, you can compute the residuals by computing a best fit line, computing the predictions. So for each row here, we have an X, which is the college percentage, and a Y, which is the median income. And we're going to predict the median income from the percentage of people in that district who have a college education. So we're going to compute the prediction for each row, the predicted income. And then the residual is the difference between the actual income minus the predicted income. And we're going to compute that for every row, and then we're going to fill in a new table. And this new table will have the prediction, the value obtained from the best fit line, and the residual, that's the error in our prediction. So you can see here the prediction was too high, so the error is negative. And there was a difference between 47,000 versus 51,000. That's an error of about 4,000. So you can see the residual is about 4,000. So residual, just another word for error. What we did here was we created a regression line. We created a regression line using the techniques we showed you before, and these fitted values, these predicted values, are computed using the regression line. Okay, so the residual is the difference between the actual value minus what you get from the regression line. All right, so to visualize this data, it can be helpful to visualize the data. So here the dark blue dots are the data. The yellow is the regression line that we computed using the techniques I've showed you in the past few lectures. So this yellow is the best fit line. And then I've showed you here in the light blue, those are the residuals, the value of the residual. It's kind of a little weird way to plot it. So for instance, for this dot here, this dot, each dot here, each row in the table represents a congressional district. For this dot here, the percentage of college-educated people who lived in that district was very high, a little over 60%. And the median income was also very high, a little over 120,000. You can notice that the actual value was larger than the prediction you would get with this regression line. So the residual would be the difference between this dot and the height of the line right there. So the difference would be maybe 22,000 or so. So it corresponds to a residual right here of about 22,000. Okay, so residuals can be positive or negative. Okay, so yeah, you can look here at the residuals. Do you see a pattern in the residuals? Is there a pattern in the residuals? Does it seem to trend, you know, kind of maybe upward or downward? Not really. Doesn't seem like there's a clear trend. Maybe there's a little bit of a, there we go. There's a little bit of like a cone shaped thing, a little bit, but it's a little hard to tell. So not a clear trend. Here's another way we can plot this. I want to do the same plot, but just show them in two separate plots because it's a little weird having them on the same plot. So maybe this is an easier way to look about things. We have one plot with the data and the fit line up here, and then another plot with the residuals. Okay, so when you look at these residuals, there's not really an obvious pattern there. Yeah, so I'm going to get to that in a bit. Will the residuals ever have a trend? Let's talk about that in a moment. So let's do another example. I just want to do another example. We're going to look at this heights data set from Galton with the predicting the height of the child of a couple. And here's the data and the linear regression fit line. And here's the plot of the residuals. And do you see any pattern in those residuals? I kind of don't. Not really. I mean, it doesn't look like it's trending with a positive association. It doesn't look like a negative association. It just looks like a blob of points. No obvious trend there to me. So what we're going to see, I'll get into this some more in a moment. Basically, if you see no trends in the residuals, that's a good sign. That's a sign that probably the data had a linear association. So using linear regression is reasonable. Okay, so those are residuals. All right, so diagnostics now. I want to talk about how you tell whether using linear regression was a good idea. I've mentioned that linear regression is appropriate when there's a linear association. So how do you know whether to use linear regression or not? You can kind of look at the scatter plot and see if the points seem to look like they're in a linear association. And if so, then linear regression might be a reasonable thing to try. And I'm going to show you some diagnostics you can use that once it looks like it's reasonable and you do the linear regression, you can kind of double check that, yeah, I think it was fine to use linear regression here. Or no, maybe in retrospect, maybe this wasn't a linear association. Maybe there's a problem with using linear regression. So I want to go view an example working with the data set the scientists who were interested in the conservation of Dugongs collected. And I don't know if I'm saying that right, but what is this? Basically it's like a manatee, but it lives in coastal waters in the Pacific area. And they were collecting data on the growth of these, and so they had a data set in their paper, and we're going to use their data set. Yet they're totally cute, aren't they? Adorable. Look like they'd be really fun to swim with. Vegetarian, not a predator. Okay, so this data set has the length of a variety of dugongs that the scientists encountered and their age. So we're going to look at how they grow as they get older. We're going to start by just visualizing the data, look at the scatter plot. So now when you look at this, do you think that using linear regression would be appropriate here to make predictions? Okay, no, why not? It kind of looks curved. It's maybe a little hard to tell, but it doesn't really look like a straight line. It kind of looks a little curvy there. Okay, so that might be an indicator that there could be a problem with using linear regression here to try to predict the length of a dugong based on its age. But let's try it anyway, even though we've kind of got this warning sign, and see what happens. We could compute the correlation coefficient. Oh, that's quite a high correlation coefficient, suggesting that age might be. I had it backwards. Here. Oh, this makes a lot more sense. I'm sorry. We can measure the length of a dugong, and then you might want to use that to predict how old it is. Sorry. So because the correlation coefficient is pretty high, that suggests that knowing the length of a dugong might be very informative at helping you make a reasonable guess at how old it is. So let's do a linear regression and look at the residuals and see what happens if you just went ahead and did linear regression here, even though it looks a little fishy. So here's the blue is the data set. The yellow is the best fit line, the regression line computed using the techniques that we've shown you so far. And if you look at the residuals, here's what the residual plot looks like. The residual plot, is there a trend here? Here, I think there's not a linear trend, but there's a very clear pattern that it's kind of bowl-shaped, isn't it? It's kind of like large on the left side, then it takes a dip in the middle, and then it kind of goes up again once you get to the far right. So when you look at this residual plot, I think it's easier to see that this is not a completely patternless blob of points, that there's this curvy, bowl-shaped, funky thing going on here. And that's a sign when you see this kind of curvy stuff that this was not a linear association, and linear regression's a little sketchy here. How do you know when to consider them outliers and when not to? Hard to say. Judgment call. If there's just one or two of them, I might be suspicious that maybe a scientist copied down the length wrong, or they started measuring and then their attention wandered, and they saw this really cool fish swim by, and then they recorded the wrong thing. But this is not just one or two, right? Like we got a fair number over here and we got a couple over here. And so maybe I might now start to suspect that maybe linear regression's not okay. Okay. So what you're looking for, you're looking for something does not to happen. If this does happen, then maybe it's not a linear association. Maybe linear regression wasn't appropriate. So let's do one more example. Let's look at the height of adults in the US. And the pattern for men and women is different. So we're going to pick just the women here. And let's visualize the data, always a good starting point. And here we can look at the association between weight and height among adult women in the US. Does it look like there's an association here? I would say, yeah, totally. Does it look like there's a linear association? Yeah, that looks like a pretty good line there. That's a line. So here's one that looks like this is linear regression. Seems like a very, very reasonable thing to do. So let's do a linear regression. Let's first look at the correlation coefficient to see how accurately we can predict weight from height. Let's see. Height, weight. Well, sure. I'm doing this the wrong table there. Okay. Whoa, correlation coefficient 0.99. Really sweet. That looks good. Okay, very promising, very promising. So now let's look at the linear regression, and let's do a diagnostic so we can just double check. We're going to do all right. So now here we have the same. Well, let's start with the linear regression. Here's the linear regression. The blue dots are the observed data, and the yellow is the fit line that goes through it. And maybe now you might start to notice there could be an issue because the blue dots are a little above on the left, and they're a little above on the right. And when you look at the residuals, oops, problem. This is a massive bowl shape, a W in double women. Good one. So this is clearly not what we're looking for from a linear regression. From a linear regression, we're looking for a patternless bunch of values, but here they're large on the left, large on the right, and small in the middle. So that's an indicator that this is not a linear association, that there's something wrong here, that this was a curvy line. And when you compare the straight line and the blue dots, you can see that the blue dots are actually curvy. And the curve is a little hard to tell, but if I was to exaggerate, it's kind of like this. And if you think about it from some physics point of view, it actually kind of, in retrospect, makes sense that if you take someone and you double their height and you double their width, then you've kind of multiplied by a factor of 4. And so maybe their weight should go up by more than a factor of 2, but maybe it should go up by a larger factor, like a factor of 4. And in fact, you get a much better fit if you do a quadratic. And if you're familiar with the BMI, what that's basically saying is the best predictor of your weight is based on kind of basically the square of your height, I guess, a quadratic function. And then BMI compares your actual weight compared to what you'd expect for your height, basically. Okay, so this is an example where it might be hard to tell from looking just the data that linear regression was problematic, but when you look at the residuals, they give you a diagnostic that helps you tell that there's something wrong with using linear regression. So if you saw this pattern in the dots here and you said, oops, I better not use linear regression, what could you use instead? What could you do instead? Quadratic, try to fit, yeah, instead try to fit a line, fit a quadratic function. And a way to fit a quadratic function would be using this nonlinear regression numerical optimization technique I showed you last lecture, or use nearest neighbor prediction. That would also be reasonable. Good. Okay, very good. All right, so let me summarize what I've said here. When you look at the scatter plot of the residuals, the sanity check is look at that scatter diagram, and it should look like a blob without patterns if the data has a linear association. So if it doesn't look like one of these patternless blobs, then that's a warning sign. If there's a nonlinear relation, you'll see some pattern there typically. And you can use this to check whether your use of linear regression was appropriate or whether there could be some warning signs. So look for curves, look for trends. If you see some outliers, look for that. If you see a change in spread, that there's a big spread on one side and a small spread on the other, kind of a cone shape, that's also a kind of a warning sign. Okay. So now I want to talk through some properties of residuals. And I think maybe the best way to show you this is by doing some examples. And then I will summarize what we found. So let's look at the residuals for the Dugong web data site. And we're going to compute the average of the residuals. Remember, I said that some residuals could be positive, some could be negative. And if you compute the average of all the residuals for all the data points for the Dugong data set, it turns out that that's 0. And if you compute the average of the residuals for the Heights data set, they're all 0. And if you compute the residuals of all the predictions for the demographics data set, they're all 0. Maybe you're seeing a pattern here. In fact, that's always what's going to happen. If you average all the residuals, the average will always be 0 whenever you do any linear regression. Whether the data has a linear association or not, you'll get an average of 0. Does anyone have any intuition why that is? Yeah. The positive errors cancel out the negative errors. Yeah, equal amount of positives and negatives. Because the best fit line kind of centers itself as best as possible around the data. It's kind of centered. So there'll be some that are above it and some that are below it. So you'll have some positive and some negative, and they'll cancel out. Yeah, that's a good intuition. Okay, here's another pattern. If you take the correlation, suppose we took this residual plot, not the original data, but the plot of the residuals, and we compute the correlation coefficient for that. Okay, so that's what we did. Took the correlation between the X value and the residuals for this Heights data set. That correlation is 0. Okay, so where was that? Way up here. Here. This plot here, if you compute the correlation coefficient for all these dots, the answer is you get 0. So let's do that for another one of these residual plots. We could do that for the Dugong. We could do that for the Women Heights residuals. We could do that for the residuals you get for any of these examples here. So let's do it for the Heights. The Heights, I think, is interesting because we said that was not a linear association. So let's see what happens for that. And the answer is you also get 0. So this is another pattern you'll find, is that if you take the residual plot and you look at the correlation coefficient of the points in the residual plot, they'll always have no correlation. So what that's telling you is there's no linear association in the residual plot. There could be some kind of curve or nonlinear association in the residual plot, but there'll be no linear association. Okay. So in general, this is always going to happen. When you take the residuals from a linear regression, it'll always be true that their mean is 0. That one consequence of that is if you take the standard deviation of the residuals, so you take all the residuals, those are a bunch of numbers, and you take the standard deviation of that set of numbers, that's equal to the RMSE. That's the RMSE of that regression line. Because if you think about it, they're defined the same way. The RMSE is defined by saying, well, we take the errors, we square them, we take the mean, we take the square root. Well, how do you take the standard deviation of the bunch of these numbers, these residuals? You say, well, take the difference between each number and the mean. What's the difference between the number and the mean? Well, 0 mean. So the difference between the number and the mean is just the number itself. So we take the difference between the number and the mean, that's the number itself. Then you square that, you take the average of that, you take the square root. It's the same thing we're doing here with RMSE. So because the mean is 0, the SD of these values is the RMSE of that fit line. Okay, so that's going to be important in a moment. Another property is there's no correlation with X. The residuals have no correlation with X. So all of the linear association, the linear correlation has been removed by the best fit line. There's no correlation with the fitted values. And this will be true no matter the data set, whether it has a linear association or something else. Okay. Well, I just showed you examples of that. So to help you get some intuition for why this is true, I got some discussion questions. So let's take the first one. Suppose that we came up with a candidate line. Maybe it's the best fit line, maybe it's not, but we have a candidate line and we computed the residuals and we found the average of the residuals was 10, plus 10 was positive. How would you adjust that line? To get a better fit, how would you adjust the line to get a better fit? Well, the residuals, remember the residual is the actual minus the line. So if the residual is positive, that means the actual was above the line we had. So the line was below the data point. So if the average residual is 10, that means that we have more positive residuals. That means our line was too low. Our line was too low. The actuals were above the line on average. So what you ought to do is you ought to raise the line. How much should you move it up by? Move it up by exactly 10. And you'll get a better fit line. So if you had a fit line and the average of the residual was plus 10, then you should move it up by 10 and you'll get a new fit line where the average of the residuals is now 0. And that's better. You want you don't want to have all of your residuals be positive. You'd like some of them to be positive and some negative. You'd like your line to be centered. Okay, so maybe that gives you some intuition why the best fit line, the average of the residuals is 0. If it was not 0, you could move it up or move it down to make it 0 and you'd get a better line. What if the residuals are positively correlated with X? I have a candidate line and I compute the residuals and the residuals are positively correlated with X. So the residuals are big when X is big and the residuals are small when X is small. How should I adjust my line to make it a better fit? Yeah, my slope was too low. Over here, my residuals were small, so my line was pretty good. But over here, the residual was large, so the points were much above my line. So my line was too low over here. So it's good here, kind of hold it fixed here, but I want to raise it up over there. How do I do that? Just kind of pivot around this point, raise it up, increase the slope. All right. So if you had any positive correlation with the residuals, you should increase the slope of your line. And if you had a negative correlation with the residuals, you should decrease the slope of your line. You get a better fit line. So anytime you had a candidate line, you might as well adjust it until there's no correlation left. And that adjustment will give you a better fit line. So hopefully that gives you some intuition why for the best fit line, there is no correlation between the residuals and the X. Now, what if, last discussion question, suppose that I have a candidate line and the residuals were above 0 in the middle, they were positive in the middle, and negative on the left and the right. How should I adjust my line? Sounds quadratic. Yeah, sounds like not a linear association. So maybe don't use a line. But suppose I still wanted to find the best fit line. I just wanted a line, darn it. How should I adjust my line to get a better fit? Maybe I can't actually. The answer is if I'm stuck with a line, I might not be able to get a better thing. So if I have a line like this and the residuals are positive in the middle, that means the data points are up here in the middle, and they're negative on the sides. That means the data points are down here and down below where you can't see. There's really nothing I can do. If I kind of go like this way, then I'm getting more error over here and less over here. That doesn't sound like a win. If I go this way, I'm getting more error over here and less error over here. Doesn't seem like a win. If I move up, I'm getting more error for these. If I move down, I'm getting more error in the middle. It's kind of like, nothing, maybe nothing I can do. Okay. So in that case, the best you could do is don't use a line, use a quadratic or something like that. Switch to some other measure. Okay, good. Very good. So we talked about previously the correlation coefficient. And what I told you was the correlation coefficient was a measure of how well the data fits a line, or how clustered the points are around a straight line. So let's try to come up with some way to quantify this, to make this numerical. All right, so I want to show you some more examples. So there's a plot of the fitted values for the heights of the child data set. And I want to do something interesting here. I want to compute some standard deviations. So what I'm going to do is I'm going to compute first the standard deviation of the fitted values of these, the y values of the points on the line. So it's like I'm taking all the points on the line, these predictions that I get for all the points in the data set, and I'm ignoring the x value. I'm just looking at the y value, just looking at the predicted height of all the children. And that's a bunch of numbers. And I'm going to compute the standard deviation of that. So that tells me how much variability there is in these predicted heights. Variability around the mean, around like maybe 67. And the answer is 1.14. And then I'm going to do the same thing for the actual heights. How much variability is there in the actual heights of the children around the mean? Be the same mean, around like maybe 67 or so. So that's taking all these blue dots, considering only the y value, not the x value. So the actual heights of all the children, and compute the standard deviation of them. And that's about 3.6 or something like that, more, which makes sense when you look at this picture here. The yellow dots are kind of close to the center, and the blue dots are more spread out around the center. So what are these measuring? They're measuring something that we can put some interpretation on. Basically, what the variability here relates to how much error there would be if we didn't know the height of the parent. Suppose you wanted to predict the height of a child, and you said, "How tall are the parents?" And I said, "I'm not going to tell you." You'd be like, "Ah, come on, man." But then you're stuck with no information about the parents or the child. This could be anywhere in this plot, and you had to make a prediction for the height of the child. Well, your best prediction would probably be the mean height of all children. That'd be the best you could do. That's kind of right in the center. So how much error would you have for that totally uninformed, ignorant prediction? Well, the error, typical error you would have, is measured by the variability in the actual heights around that mean. And that variability is measured by the standard deviation. So the standard deviation of the actual values is 3.6 value, tells you about how far off you would typically be if you made that ignorant prediction without knowing the height of the parent. 3.6 inches would be a standard deviation. That'd be a typical kind of error. Okay, and you can see that the yellow line has less variability around that mean. Now, what about the error if you make a prediction knowing the height of the parents? Well, that will have to do with the residual. The residual is the error. It's the difference between this prediction and the actual. So for each child, we get a residual value. That's the error value. And we can compute the standard deviation of that the variability of those residual values. And that would tell you about how much error you make if you make a prediction with knowing the height of the parent. Okay, so the standard deviation of the actual values is like the error in an ignorant prediction. And the standard deviation of the residuals is like the error in an informed prediction, informed by the height of the parents. Okay, so we could look at how much your prediction error decreases when I give you the information about the height of the parents. And that's going to tell you something about how informative the height of the parents there is, or how closely these are associated. It's going to be useful for analyzing this, this prediction stuff. Okay, so we got the standard deviation of the actual values, the standard deviation of the fitted values, and the standard deviation of the residuals. Those are three different standard deviations. We're going to look at how they relate. Hopefully I gave you some intuition for why we might care about those. So let's start with the standard deviation of the actuals and the standard deviation of the fitted values and see how they relate. And I computed that the standard deviation of the predictions was 1.1, and the standard deviation of the actuals is 3.6. And so let's look at the ratio between those two. The ratio between those two is this is about a third of this. Now I'm going to compute for you the correlation coefficient, and you might notice something interesting here, that this 1/3, the correlation is also about 1/3. So I picked this. There's a reason I picked this. So maybe you're getting suspicious. Is that a coincidence that these two are so similar? It's not a coincidence. And I'm going to do another example to prove it to you. I'm going to do the same thing for the Dugong data set. And I'm going to look at the ratio between the standard deviation of the fitted values, the predictions, and the standard deviation of the actual values. And that's about 0.83 for the Dugongs. And for the Dugongs, the correlation is also about 0.83. So this is a general property. This is a general property that the ratio between these two standard deviations is always equal to the correlation coefficient. And let's see, well, almost. It looks like we're seeing a very clear pattern here. The ratio between these two standard deviations is equal to the correlation coefficient. And that's almost true, but with a little asterisk. So let me show you the asterisk. I'm going to do that with one more example of a data set. This taken from cars. So this is, we looked at this data set before. This is a bunch of cars, and these are the hybrid cars. And here we have different stuff, and we have the mileage, miles per gallon you get, and we have the amount of acceleration, the maximum amount of acceleration you can get from this car. And we're going to do a linear regression between those two. And you can see that there appears to be some relationship here between the two of them. The cars with a higher acceleration get worse gas mileage. No surprise. Okay. Now, if we look at the diagnostics for this linear regression, the residual plot, you can see here that this residual plot doesn't appear to have any systematic upward or downward, but what it has is this cone-shaped thing going on, like this kind of a sideways pyramid. And that's an indicator it's not a patternless blob. So that's an indicator there are some issues. This is a little bit of a red flag warning, just as a side note. This is, if you care, it's called heteroscedasticity. You don't need to know that for this course. So that's a little bit of a potential caveat. But we're going to go ahead and we're going to use the linear regression anyway, despite the caveat. And we're going to look at the correlation coefficient, and we're going to look at the ratio between these standard deviations. So there's the correlation coefficient. It's negative this time, negative 0.5, because this is a negative association. That's a downward sloping line. And then we're going to look at the ratio between the standard deviation of the fitted values, the predicted values, and the standard deviation of the actuals. If we look at that ratio, by our previous pattern, this should be negative 0.5. But wait, it can't be negative because standard deviations are always positive. So the ratio of two positive things has got to be positive. So here we see, well, it's not quite the same as the correlation coefficient. It's the negation of the correlation coefficient. See, the ratio of standard deviation is always positive. The correlation coefficient can be positive or negative. So now we can correct what the pattern we're seeing is. These two are always equal, except if one's negative, then this is the negation of that. So that's right. It's the absolute value. All right. So the pattern that we're seeing here is that the standard deviation of the fitted values divided by the standard deviation of the actual values is always equal to the absolute value of the correlation coefficient. And that is correct. That is a true pattern that will always hold for any linear regression. Okay, so let's do a little math and summarize what we found. I'm not going to try to prove this to you. One can prove it mathematically, but I just wanted to show you these examples, and hopefully from the patterns you saw in the examples, it's plausible to you that this would always be true. And I'll promise you, you could just take it on faith. It's always true that the standard deviation of the fitted values divided by the standard deviation of the actual values, the actual y values, the observed values, that ratio is always equal to the absolute value of the correlation coefficient. Or if we multiply both sides by that denominator, another way to put this is the standard deviation of the fitted values is equal to the absolute value of the correlation coefficient times the standard deviation of the observed values. And I know this is a lot. Like, this is gonna, for me, when I saw this, this was like, why do I care again? This is weird. This is confusing. I'm lost. There's 3 standard deviations. We're looking at ratios. I don't understand why we're doing this. So if you're a little lost in the math, it's okay. I'm going to tell you why you should care in a little bit. So let me reframe this equation here. I'm going to square both sides, and this is going to take another form here. So I'm going to square both sides, and that's going to give me another equation here. And we're going to use, that's going to tell me something about the variance. And the variance is just the square of the standard deviation. We've been using the standard deviation, which is nice. The variance is a little harder to interpret, but has some good properties. And so what we obtain is that the variance of the fitted values divided by the variance of the observed values is equal to r squared, the square of the correlation coefficient. So this statement about standard deviations, there's a corresponding statement about variances. And this is going to help us look at the amounts of the errors. Remember, the observed value is equal to the fitted value plus the residual. So the residual is the difference between the observed and the fitted value. Okay, so now you might be really tempted to think that the standard deviation of the y values is equal to the standard deviation of the fitted values plus the standard deviation of the residuals. That would be intuitive, but wrong. Sadly, it's not quite right. It's not quite right. But what is right is that the variance of the y values, of the observed values, is equal to the variance of the fitted values plus the variance of the residuals. So why am I showing you this equation? The reason I'm showing you this equation is because 2 of these 3 variances are things we care about. The variance of the fitted values, who cares? Whatever. But the variance of the y values, the variance of the observed values, or the SD of the y values, that's something we care about. That's the typical error if you had to predict without knowing X. And the variance of the residuals, or the SD of the residuals, that's the RMSE. That's the typical error if you did know the X value and had to make a prediction with knowing the X value. Okay, so comparing the standard deviation of y and the standard deviation of the residual is going to tell you how much you gained by knowing X, how much more of an accurate prediction that helped you make. So because the equation, we care about the SDs, the equation is nice with the variances. So we'll kind of do our calculations with the variances, then we'll convert to an SD, and the SD is something we care about and we know how to interpret. So absolutely yes in the chat. If you take this equation, you could take the square root of both sides. The square root of the left side is the standard deviation of y. And the square root of the right side is the square root of the sum of these 2 variances. Or another way to say it is the sum of the squares of these 2 SDs. Whew. Yes, the fitted values are the predicted values. The prediction we make with linear regression is based on the fit line. Okay, so this is called a variance decomposition. That's the equation, this equation up here. You can just memorize this if you want. And so a consequence, we'd said previously, the variance of the fitted values divided by the variance of the observed values is r squared. So the correlation coefficient tells us about the ratio between the variance of the fitted values and the variance of the observed values. That means that from that, you can infer that the variance of the residuals divided by the variance of the observed values is 1 minus r squared. So you divide both of these sides, both sides of this equation by the variance, then the left side will be 1. This will be r squared. So this has to be 1 minus r squared when you divide by the variance of y. So this last equation now is one we care about. It says the variance of the residuals, that's the error when you make a prediction knowing X, divided by the variance of y, that's the error when you make a prediction without knowing x, is 1 minus r squared. So now we're ready to do a little interpretation. If r is close to 1, if the correlation coefficient is close to 1, then 1 minus r squared will be 1 minus something that's almost 1. So this value, 1 minus r squared, will be very small, be close to 0. So this ratio will be very small, which is saying that the error, once you know x, is much smaller than the error without knowing x. So knowing x really helped. So if r is close to 1, that means you have a strong association, and knowing x really helps you make a prediction, really reduces the amount of error in your prediction. And if r, the correlation coefficient, is close to 0, r squared will be close to 0. 1 minus r squared will be close to 1. So what this is telling you is the error in your prediction when you know x will be almost as large as the error if you didn't know x. So if the correlation coefficient is 0, then making a prediction using linear regression, knowing x didn't really help you very much. That's what these equations are showing you. Okay, so I showed you this equation with respect to the variances. We can now look at this with respect to the standard deviations. If I take the square root of both sides and divide, this tells me that the SD of the residuals, so here's the formula you could memorize if you wanted to memorize one and didn't want to try to have to follow this derivation. This derivation didn't make any sense. Memorize this formula. The SD of the residuals is equal to the square root of 1 minus r squared times the SD of the observed values. Okay, so if you know r, that tells you how much the SD is going to be reduced. All right, let's look at some example code. All right, so there's our formula. We're going to do this now with the Galton Heights data set. And we've got a plot here. And I'm showing you here a blue line, which is the mean, which is the prediction you would make if you didn't know the height of the parent. And then the yellow line is the prediction you would make if you do know the height of the parent. And if we compute the standard deviation of the actual heights of the children, that's 13. Well, that's the variance, actually. The variance is 13. The variance of the heights of the children is 13. The variance in the residuals is about 11.4. And the variance in the fitted value is about 1.3. And you can see the 1.3 plus 11.5, I guess, is 12.8, which is the variance of the heights of the child. So that's our variance decomposition there. This variance is equal to the sum of these two variances. And we could do the same thing for the Dugongs. We could look at the variance of the actuals, the variance of the fitteds, and the variance of the residuals. And here 18 plus 41 is about 59. So this variance is the sum of these two variances. And if we look at the correlation coefficient and we use this equation, we multiply the square root of 1 minus r squared by the variance, the standard deviation of the actual heights, you get 3.38. So that is what you would predict to be the SD of this residuals by our formula. And let's check it. Let's actually compute the SD of the residuals. Did I compute the SD of the residuals? Maybe I need to compute that. Residuals, heights. And I get the same value. Okay, so the SD of the residuals was indeed what this formula predicts. Or I could use the correlation coefficient for my hybrid cars. It was negative 0.506. And use the formula, square root of 1 minus r squared times the standard deviation of the actual values, the observed values. That would tell me 9.4. And now I look at the SD of the residuals from the linear regression, and that's 9.4. Okay, so interpretation for you. You now know a formula that will let you compute the SD of the residuals from the SD of the actual values. So that means if you know what the correlation coefficient is, and you know how much variation there is in the actual values, you can predict the error in your estimate, the SD and the residuals. You'll be able to tell how accurate your estimate will be. How much of an error will you get if you use linear regression to make a prediction? And all you need to know to figure that out is you need to know R, the correlation coefficient, and you need to know the amount of variation in the Y values. Okay, I think we'll stop here. So this is a way that you can think about how accurate your linear regression is going to be, and a way to interpret the correlation coefficient, a reason why the correlation coefficient is really important. It helps you tell how much the linear regression prediction will help you reduce the error in your predictions. Have a great weekend. Don't forget to do the homework and the project. See you on Monday.